Hello guys, this is the continuation of the lectures on proving methods. This is the part 2, and in this lecture we're not actually going into hardcore proving methods by discipline, by sub-disciplines in mathematics. We're still using, or will be examining, the most rudimentary ways in which we prove things in mathematics. The most important parts of today's lecture will be proof by contradiction, and some statements of mathematical induction will be going off general mathematical induction, mathematical induction as it is most famously stated, and we will leave strong mathematical induction. Important things we will be viewing in today's lecture, and the most important things we have learned in previous lecture were proved by cases and direct proof, and I'll be showing some references to that, so I hope that people have remembered something from the previous lectures. If not, they can just raise their hand or speak, and I will help them remember, I suppose. So, where is my mouse? So, proving methods part 2, we will start by counterexamples. I think that a lot of people already intuitively know what counterexamples are, so this will not come as any surprise, but in order for us to be concise about proving methods, we have to go over them. So when we have statements in the formulation that is in this on the board right now, on the slide, what we are trying to find is the existence of an x, which is still an element of S, such that not x is true, right? And if we find such an x, it is called a counterexample. Later on, when we will be examining existence proofs and disproving existence statements, I will be referring back to counterexamples, so I think that people should remember how the formulation of counterexamples is formulated currently. So this is very intuitive. It will not be something, it's not hard, but for the sake of conciseness, we will go over it, right? So this is a rudimentary example in an example. So if we have a statement such that it encompasses if x is an element of real numbers, then this inequality follows. What we want to show here is precisely the formulation in which this doesn't apply. Some of you who are more acutely aware of what is happening in the general presentation might already see the counterexample which we will be showing here. By the way, just a small thing. Stone, do you see what is being shown on the slides right now?
Well, I was about to say, it seemed to be transitioning from the counterexample slide to the introductory slide, and currently it's on the introductory slide.
Oh, why is it not working again? It should be on counterexamples now.
Yeah, now I see counterexamples.
Okay, yeah, then I'll stay here. So I don't know what happened. I just saw on the stream that it wasn't. Right, so some of you may already see what we will be showing. The critical part here is precisely the inequality itself. Right, so does anyone have an idea maybe what the counterexample might be here, knowing the crucial part? Well, I see that it's just two people here, so I suppose no one will. Right, so we have the solution. I will be presenting it and then I'll showing the solution. Right, the crucial part is that we have a square of something. The square of anything in real numbers is equal or greater than 0. Since we know that the square must be greater or equal to 0, we must find when it is equal to 0. And the only way in which a square is equal to 0 is that what is being squared is equal to 0. In this case, x to the power of 2, more precisely x squared, minus 1 must be equal to 0. And this happens only if x squared is equal to 1 or minus 1. For the purposes of this example, it is only necessary for us to show one counterexample, even though in this particular case, two exist. And this is the solution we come to find. Does anyone maybe have questions? This is very straightforward. It's not much complicated. Okay, I suppose not. Then we will be going proof by contradiction. The proof by contradiction might be the most common way in which we prove things in mathematics. I already assume that a lot of you have already been introduced to some formulation of what it means to prove by contradiction. And what I'll be stating is just a more concise presentation of what you already probably know. So when we have a statement, suppose that we want to show that some statement R is true, right? When we want to what the methodology is behind the contradiction is that we are assuming that R is false, right? We are assuming that the statement we want to show true is in fact false. And if by that assumption we are able to arrive, or in this case maybe deduce, maybe inductively infer, or we already know that statement, that negative statement, so not R in this case, connotates with it something which we are assuming to be true, but are in fact in the negative wrong, or are in conflict with some other fact, axiom, or something which we have taken. So that derives us at the contradiction, right? If we denote the assumption of the known fact which is superseded, which is already necessary for us to even examine this as P, right? So we know that it is true, it must be true, and then we have deduced it from the negative example that the negation of it implies that not P is true. Then the conclusion, the contradiction, is in fact pretty obvious. What we have established is that P and not P are simultaneously occurring, which is the definitionary representation of a contradiction. So I think that this is very straightforward, right? We have deduced not P, and we know that P is true, right? How we know that P is true? It would be an assumption of the proposition. It can be a known fact. It can be an axiom. It can be a lot of things, right? So we have deduced these two things. These two things are simultaneously occurring within the contradiction, and that is precisely what we don't want. And this defines what a contradiction is. Now we go into a more of an implicational understanding of what it means here. So we know that the statement not R, right, our negation, our false statement here implies the contradiction. So this is the C that I'm talking about, and R is this thing here, right? The R is a false statement. Since we have this implication, we know that implication itself is true, because we know that by virtue of R, we inherently get 2C. And we know that C is false, right? It cannot be true because it is a contradiction. And then you can think of truth tables. In the next slide, I will show you the truth tables. And if anyone has questions maybe about what this means in implicational understanding, like in truth tables, I can explain it there. But generally, if the implication is true and the conclusion is false, it follows that R must also be false. Any questions, maybe? I suppose not. This is the truth tables here, right? And so we know that the implication is true, so we know that this, and this implies. The next thing we know is that the conclusion is false, so we have these things here. Since the only way in which these two things coincide is when the statement and R is false, here, that means that NR is false, right? This is pretty much obvious. And since NR is false, that means that R is true. Otherwise, we would be having another contradiction. Okay. Let's take an example. There is no smallest real number. Does anyone maybe have an idea how we would approach this statement? A big hint is, of course, that we will be using proof by contradiction here. Okay, so the solution is that we are, of course, assuming that to the contrary, and that is that there is a smallest real number. In this case, we will be denoting it as R. R is a placeholder, it doesn't matter what it is as long as it is a real number. So it is some number R, which is an element of real numbers, that is the smallest number. Since we can infer this triple inequality that 0 is lesser to R half and R half is lesser to R, it follows that R half is a real number that is also smaller than R. But this is a contradiction, and the contradiction is precisely because of our assumption here that there is a smallest real number, and that number, so the smallest real number is R, and we have shown that R half is the smallest real number, and both of these things cannot be simultaneously occurring within R, and that's a contradiction. It's a very straightforward, it's nothing very complex, and yeah, I hope that this is understood. If someone has questions, they can always ask. But yeah, this is the general presentations of what is occurring here.
Yeah, so the contradiction is that R is and isn't the smallest number?
Not precisely, but yeah, in sentiment, yes. You can. It is shown that R half is the smallest number and that R is the smallest number. So we have two smallest numbers. That's the contradiction.
Right. It seems like it was affirmed that R is the smallest number, but then we just saw that we can have R2, which would be smaller than R, which would make that the smallest number, so we can't have R being the smallest number when there's another smaller number.
Yeah, and it's not 2R, it's R half, but yeah, the general idea is that it is not that R is two things, it is that smallest things is two things. So there are two smallest things. And that's kind of a mathematical contradiction, right? We can get to philosophy here and say that there can be two smallest things, but I think that's nonsensical, probably, right? And in mathematics, there is one smallest thing generally.
Right.
And this is within the field of real numbers. That's the important part.
Yeah, I get that. Yeah, I think that just leads to a contradiction. It's like me saying that we're both taller than each other. That just wouldn't work.
Yeah, precisely. Two things are taller than each other, right? But it will be a similar thing, yeah. Well, I think this is understood, yes? Do you have any questions?
Makes sense to me.
Okay, then we'll be going into the next one. And next one is an example. And this is the famous example. With this example, you have had fights in mathematics for centuries, from Greeks to Renaissance to Dark Ages. A lot of mathematicians really hated irrationals. Pythagoreans famously thought it to be devils or something like unholy. Descartes didn't recognize them. He didn't even consider them numbers, if I'm remembering correctly. The same is true with Descartes and negative numbers. So yeah, a lot of fighting has been done with irrational numbers. And this is, I think, among the most famous examples because it can be shown with a lot of different proving methodologies, right? You can show that the square root of 2 is an irrational number by a lot of different ways. What we will be showing here is a sort of proof by cases, and we'll also be using contradiction, of course, because we want to show the contradiction. Maybe someone already has an idea how they would solve this, knowing the methodology that is presented, namely that they have to use proof by cases and contradiction. Does anyone have an idea, maybe? I suppose it's too early for this. The next exercise one might be more appropriate for these kinds of questions. Right. So the solution is actually very simple. What we are doing is we are assuming to the contrary, right? And that is the first thing we always do when we're trying to when we're using contradiction. So when someone says show by virtue of contradiction, and you are in a class of mathematics, that something is something, right? Whatever the fuck is happening. What you always have to do is assume to the contrary, because that is the presentable methodology of it. Uh, Another example, which is often confused in mathematical language, and I have seen a lot of people been talking about this, is that you have shown by virtue of mathematical methodology that something is contradictory because you have shown that this contradicts with some known fact. This is, in fact, not a contradiction. It is a contradiction, but it's not a mathematical proving method of contradiction. Let me come a couple of slides before. Proof by contradiction necessitates that we have to presuppose or suppose that the R is a false statement. We want to show R is true statement. If you're purposely just showing a proposition to be in conflict with another proposition, you're not in the realm of mathematics, you're in the realm of something else. Possibly logic, possibly epistemology, possibly whatever the fuck, right? You're showing propositions. This is a contradiction, but it is not a proof by contradiction. Does it make sense? I'll take that as an affirmative. Okay, let's get back. So the real thing which you have to always have in mind is that when you're asked in mathematics to prove something by contradiction, by method of contradiction, you are not allowed to just say this is contradicting to a fact. You have to show that if you assume to the contrary, that it leads to a contradiction. That's the important part. Okay, what we're doing here is that we're assuming to the contrary, and the contrary of this statement is the saying that the square root of 2 is actually rational. Now, this part here, I am fairly confident that if you have been breaking, isn't it? Is my mic breaking? Hello? I think it's okay now. Right. In in Introduction to Mathematics, if you have done some very very beginner level number theory or just any course in anything with relation to rational numbers, I think that even in middle school you should be thinking this. So if something is a rational number, it can be depicted by this very formula here, where a and b are integers. In more precise formulations, if you want to be very nitpicky, you can say that a is an integer and b is a natural number, but it doesn't change anything. It's just usually that in literature, as far as I have been seeing it, it is that the upper level of a fraction is always taken to be an integer, and the lower level of fraction is taken to be a real number. The important part here is to denote that the b is not equal to 0, because then you get to problems in mathematics, right? The lower level of a fraction is never 0, at least in real number analysis, right? Any questions about this? This is very important to understand. It denotes a crucial difference between rationals and irrationals. Okay, I think that people are following thus far. This sentence, which is following, is the most crucial sentence of the proof. From the previous lectures, the previous lecture on mathematical proving methods, I explained what vlog is. It is without loss of generality. It just means that we are presupposing something, and that presupposition, that supposition, is not affecting our proving methodology at all. Okay. In this case, what the without loss of generality is referring to is that we can assume that the fraction a over b is reduced to the lowest terms. Reducing to the lowest terms in mathematical methodology means that the two numbers do not have the shared divider. There is no number which divides the first number and the second number in natural numbers except the number 1. Okay, this is the most crucial. I hope that you keep this in mind. I will, of course, refer when necessary to this statement, but keep in mind that the crucial statement in this proof is precisely the statement that is denoted without loss of generality. The next step is also a referral to what we have learned in the previous lecture about even and odd numbers. But let's take it a step of the time. This here, you might have it confused how someone might get to this. This is just, of course, the restatement of this equation here, but we have squared every side of the equation. So square root of 2 to the power of 2 is 2, and these two squared are as expressed here. I hope that everyone is familiar with how squaring works, so then I don't have to explain this. If not, it is a very general rule in how power works. And when I say power, I don't mean strength, I mean to the power of. Okay, so if we multiply this equation by b squared, we get that a squared is equal to 2 times b squared. This is the crucial part, because you have to remember from the previous lecture that this is precisely the demarcation, the formulation of the expression such so that it expresses that a squared is an even number. And the another part to consider is, of course, that b squared is also an integer. And b squared is an integer from this, right? Another thing is that if you're following very acutely, if you're following what I have been saying very attentively, you can know that I said that b can be a natural number. Then this is not an integer. However, every natural number is an integer, but not every integer is a natural number. So this doesn't really turn itself. The other thing is this part here, right? This is another thing which you might have. This here, right, is a thing you might not be familiar with, and I will not be showing this. But let's take it for granted, for the sake of this presentation, that we know this. That a theorem which states that if a to the power of 2 is even, and then a itself is even. This is a theorem. We can prove it some other time if necessary, but for the purposes of this presentation, we will be taking it as known, of course. So if a is even, we can denote it in this formulation here, right? This is the same. I don't want to be repeating myself, but if every time you see this demarcation, you can assume that a is even. Of course, knowing that c is also an integer, this means that c is an integer. Now, if we induce this in our equations previously, so we are using this and putting it here in this. Instead of a, we are using 2c. We're getting this equality. This equality with simple algebra gets us to b squared being equal to 2c squared. However, what does this mean? Does anyone know what does this mean? It's a very important thing to always keep in mind with these kinds of proofs. is what does it mean for a number to be odd and what does it mean for a number to be even. In this case, we have shown that b squared is even, and by the theorem here, which we will not be showing, we know that therefore b is even. And since both a and b are even, they necessarily have a common divisor, and that being precisely 2. And now, what is the contradiction? The contradiction is that since we have assumed by virtue of log that there is no common divisor, and now there is a common divisor. So the contradiction is that there is and isn't a common divisor. And since this cannot be, we know that the real number square root of 2 is irrational. Make sense? Okay. This is an exercise. This now will go into existence proofs. There is a thing in mathematics which is called an existence theorem, which is essentially just a statement. It's not really a theorem, so to say, but I suppose we will be going as an existence theorem. And it states that an existence of an object or objects possessing some property is asserted. That means that an existence theorem is concerning an open statement Rx over the domain of S. So this is the precise formulation of the existence theorem. It states that there exists an X, which is an element of some domain S, some set of S, such so that Rx obtains. And it's really simple. A proof of existence theorem is thus very, very intuitive. If we want to show that something exists, the simple presentation which ascertains this fact is that we show at least one thing which exists such in the domain of S, such that the R of X, the statement, the implication, whatever, obtains. Very simple. You do not have to show this by counterexample or by example or something. You can show this by other proving methods. For example, a direct proof, you can show that it must be that something like which in the domain of S of the desired type exists, regardless of you being able to show that it exists. This is a much more complicated way and is usually requiring you to use other proving methodologies, and is a more common way of proving things. At least in higher advanced mathematics, you will not always be able to construct in yourself an ideal, an example of a thing which has the properties of the domain such so that Rx obtains. The most simple one, this is like a very simple example of what is meant here, that there exists an integer whose cube equals its square. I think that you should be able to find this very easily. Does anyone have an idea which integer might that be? Okay, for a cube, I think that everyone knows what cube and square mean, so probably just shy. The obvious number is number 1. 1 plus 1 cubed is equal to 1 squared. So that's our example. So the thing here is, the important thing to consider here is that 1 is in the domain of integers and has the property such that it satisfies what is Rx in this case, and that being its cube being equal to its square. Very intuitive, very easy. I don't think that there should be any problems here. If anyone has questions, of course, they can ask, and I'll be going to the next slide. This one here is a more complex way of existence proofs. you might, at first, when you see the solution, be confused how it is an existence proof. But if that question arises, you can of course ask me, but it should be pretty visible, I think. And this also uses proof by cases. So the number we will be choosing in this case, since we have there exists irrational numbers, we're assuming the existence of multiple entities. And in this case, A and B, we need to assume an example of A and B. In this case, we will be using square root of 2 and square root of 2, since we need to use irrationals, right? And we have shown today that square root of 2 is an irrational number, so to not go into any more complex numbers, and it will be the most easier number to show, square root of 2 is our candidate. It is oftentimes very hard to conceptualize this, so it's to often find an example, not to conceptualize it. It's always hard. In this case, it's always hard because to show an example of something is you have to have a lot of training. You have to know methodology quite well to be familiar with the task at hand. So we have two cases. The first case is a quite obvious one, that square root of 2 to the power of square root of 2 is irrational. Well, it's pretty obvious that if this is rational, then we have satisfied the Rx here, right? We have shown it. Done. Case 1 closed. Easy peasy. Done. The second one is a bit more challenging, and it's the one that this proving method is concerned with. And that is when this number is irrational. Then what we do is, what if we take another number? And put that number to the power of 2. So now we have square root of 2 to the power of square root of 2 to the power of square root of 2. Now what we know is that square root of 2 times square root of 2 is 2, and square root of 2 squared is 2. And that is, of course, a rational number. And thus we have shown this. Now, in this case, there is a small thing which might escape the grasp at first. And it is a big question here, and I would like to see if people here have found it. What's the big thing in case 2 which might be confusing? I will give you a hint. It's relating to this. Okay, no one seems to have an idea. Okay, if we are taking two irrational numbers, how did we get to 2 here? 2 is obviously rational. So how did we get to square root of 2 to the power of 2? We can't take 2 because 2 is obviously rational. So we do not have two rational numbers. We have an irrational number and a rational number. Well, the solution is very obvious. Since a is equal to square root of 2 to the power of square root of 2, what we have here is a rational number by assumption. So this is the assumption. The second part is that b is equal to square root of 2. And since we know that square root of 2 is irrational, we do not have two rational numbers. Even though in concert they might be, it's inconsequential. So what we have here is, with the simple usage of algebra, we have managed to reduce the stated case of a formula here to something which obviously results in a rational number. So we have resulted in b, quote unquote, being a rational number, but in fact it's not b which is irrational, but the concert, the fusion of a and b, which results in a sort of trickery that gives us the impression that we might be mistaken. But yeah, I kind of made it more complex than it needs to be. I just wanted to see if people might be confused with what I was saying and kind of explain it in more detail. Maybe to people, what I've been saying is kind of gibberish. They already knew this, but yeah, if anyone has any questions, I suppose now is a good time. This is not a. It's an important example to. I suppose that there is no questions. Okay, the next one is disproving existence statements. Thus far, we have been proving by methods. Now we're disproving by a method. An existence statement, we have already shown what an existence statement is. So this would be without this here is an existence statement. We want to disprove it, so we want to show its negation being true. And a negation of this statement is sorry. This is not a sign of equal, but the same as saying that for every x in the domain of S, not x, not R of x, right? And if we want to show, to disprove the existence statement, what is being asked for us, because this would be a very hard thing, a challenging thing to do, because we would be using the previous methodology, but proving the negation of it by existence, and it doesn't follow, because it would not be. It would be like using counterexamples. It would be a criminal case of misusage. Because there is a similar thing if the referral is obviously to the previous point of counterexamples. In counterexamples, we had this statement, and this statement was in our proving methodology of counterexamples. But now that we are not in, this is very similar to it, and since it is similar, we can kind of use similar intuitions which guided us in our understanding of counterexamples to deduce the way in which we will be conducing ourselves, managing ourselves in this example, in this methodology. So what we want to do is we want to show, as we have shown with counterexamples, that this statement is true, that for every x, the statement, the negation of a statement is true. And if we manage to show this, we have disproven the existence statement, because we have shown the existence statement being false. And if the existence statement is false, we have disproven that the existence statement. Okay. The very easy way to show this is by an example. You can, if you have been here on the previous the previous lecture, the introductory one, you are already familiar with this. What is being used here is what methodology? Does anyone know? Well, it's two. The first one is, of course, disproving existence statement. That is the first obvious one methodology. The second one is a more challenging one. Not challenging one, but from the previous. It's a direct proof, right? Well, the solution is as you have already seen in the previous lecture, is that we now show that if n is an odd integer, then the not Rx, right? And not Rx is that this statement, this n to the power of 2 plus 2n plus 3 is even. And this is the negation of it being odd. And if we can show this to be true for every possible n in integers, right? The crucial part is that it necessarily has to be in the domain. It needs to be in the domain. Domain needs to be shared. You see the domain. Domain needs to be shared. The domain, in this case, is integers. And if we can show that for every integer, the statement is true, the negative of the statement is true, then we have successfully disproven the existence statement. Since I have shown like 7 examples of this, the easy solution is that since we know that the n is an odd integer, we replace it with this. This is from the previous lecture. This is just a formulation of what it means to be odd, and by simple algebra we get to this. A k here is obviously a placeholder. This is all from the previous lecture, so I will not be dwelling on it too much. And this formulation is the formulation of what it means for a number to be even. Just a small reminder, this whole statement in brackets we can make into a placeholder u. Why, if you want to know why in more detail, check out the previous lecture. And now we get to the statement being even, and this is now even for every possible n, for every odd integer, right? For every n such that it is odd and an integer. This is the domain we are looking in. This is the important part. And now this is done. Tutto finito, chef's kiss. Mwah, done. This is how you disprove existence statements. Now we are going to the big boys. We are now entering the big leagues, the mathematical induction. The first is the most famous presentation of what it means for mathematical induction. Mathematical induction is a methodology, but unlike previous methodologies, it is proven by previous methodologies, right? It is a methodology which is proven to be true by previous methodologies within mathematics. There are a couple of formulations of it. In today's lectures, I'll be going the most famous one, and that is for natural numbers. The general one and the strong one I will leave for the next lecture, so that we do not have, so that I don't take too much time. I already spent 45 minutes on this, and this might go long depending on how it goes. The important part to remember about mathematical induction, that contrary to its name, it is not actually an inductive argument. It's deductive. That's an important part. Now to get to what it means. The principle of mathematical induction, it's a theorem. It states that for every positive integer n. Now, there is a small word play here, which might confuse some other people, because depending on your area, if you're American, then, or maybe not American, but if you're in some fields of mathematics, 0 is considered to be a natural number. In most cases, in most of relevant fields, it is not. And since it is not, and I have, in my country, it's never been that 0 is an integer, not an integer, but a natural number. So it's usually, you can find it in literature to be stated for every natural number. Natural numbers go from 1 to infinity, right? And in mathematics, you will usually find it being stated that 0 is a non-negative number. And if you have like a big logic brain, that might be that it's a positive number. No, that's not how it goes. It's just a non-negative number. It's not positive, right? And of course, depending on the literature. So to be safe, I presented it for each positive integer n. And in every literature, 0 is taken to be non-negative, so this follows, right? And you can think of it like natural numbers if that helps, but counting numbers, right? Maybe that's how you depicted it in your school, counting numbers. So for every positive integer n, let Pn be a statement, and if that statement satisfies the conditions 1 and 2, then Pn is true for every positive integer n. The statements are very, very simple. The first one is stating that the first number in the sequence of numbers, if you're familiar, of course, I will have to familiarize you with the principle of the well-ordering principle, right? It means the least element. If the least element, in this case, the least element of natural numbers is 1. If the least element is true, this is the first. The first condition is least element. The P of least element is true. The second is that the implication, which states that for some k in n, k must be greater than 1 in this case, but it's a placeholder. It doesn't really matter, right? If the implication which states that if pk, then pk plus 1 is true, if these two conditions are met, we are done. I will now show the proof of this methodology, and later on I will be giving you a more language which is used in tasks in when people use mathematical induction, and we'll explain the general methodology when relating to precise tasks. Of course, now we get to proof, and the proof is done by contradiction. I have explained what contradiction is in mathematics, what proof by contradiction is in mathematics, but I will repeat so it settles down that showing a contradiction and showing by contradiction is totally different. Proving method of contradiction is showing a contradiction. So when you say that the proposition is in contradiction, you have not used the method of contradiction. You have just shown a contradiction. In this case, we are using a method of contradiction, right? We're using a proof by contradiction. And the necessary requirement for that is that we need to assume the theorem is false. So if these two conditions are satisfied, then there exists a positive integer n for which Pn is false. Is a false statement, right? The thing that will help us in this is that we need to categorize. We need to group all the elements which have this property. So every n, which is an element of natural numbers, such that in this case, you see here, n is natural numbers, right? In this proof, they have assumed what I have been saying, and that is that every positive integer, and that to them is natural numbers, right? In methodology, this is quite important. If they wanted to be consistent here, right? If the proof wanted to be consistent, they would have to say n such that an element of elements, right, of a set of things which is greater than zero, right, and being greater than zero. But this is general proof, right? In literature, you will always, like in 99% of literature, you will find here in most famous presentations of principle of mathematical induction, usage of natural numbers. Just a small notation, not to be confused. So we are collecting all elements which have the property that they are natural numbers and that for them the statement is false. Okay, now I have to introduce you to the well-ordering principle. The well-ordering principle is saying that in the set of things there exists a least element. So if there exists a least element in a set, that set is well-ordered. The most famous implications and usages of well-ordering principles are used in depictions of what it means for a set of things to be the set of natural numbers. Oftentimes you will find it something like in literature to be explaining that well-ordering principle is a principle which states that natural numbers are well-ordered and therefore everything is well-ordered, something like that. They're tying the definition of well-ordering principle to natural numbers, which is something that has been done in many different ways, many different principles, such as how we know that that some infinities are countable and not countable. This is also tied to the concept of natural numbers, similar to the well-ordering principle. But in this case, the important part, since we already have that this is a natural number, I will just try to explain the principle, is that we have to have the least element. Natural numbers necessarily have the least element, and that is the element 1. Okay? Since S is a non-empty subset of N, now here is $1 million question, right? If anyone knows, why do we know that S is non-empty? Does anyone have an idea? I guess not. Okay. Because the statement itself is stating that there exists some positive integer n. So there exists at least one integer n. And that means that it is a non-empty set, a subset of n, right? And since we have one, it doesn't say how many of them are. They're saying that there exists at least one. Does that make sense? I'll take that as a yes. We will denote the least element of our big S, the big boy S, as the small s. I will always say big S and small s when I'm speaking, so just to explain the notations here. Since we know that P1 is true from the conditions, right, from the statement the statement we're trying to prove, since we know that P1 is true, then we necessarily know that 1 is not the element of S. Okay. Now that we have that S is greater, or now we know that S is greater or equal to 2. How do we know this? This is pretty simple. If S is natural numbers and S is not 1, then it necessarily means that S is greater or equal to 2, given no other conditions. Now, the part which always confuses people is how do we get that S minus 1 is is element of n. This is a linchpin here, so I would like to see if someone has an idea, maybe something about why S minus 1 is now equal an element of n.
Because if S is equal to or greater than 2, then the lowest it can be is 1, which is the lowest possible number for natural numbers. And if it's greater than 2, then it's also going to be a natural number.
Precisely. Correct. It is as you say, the natural number, because S, the small s, are all elements of natural numbers, and the least element of the big S is possibly 2. I give possibly, quote unquote. The least possible is 2, and 2 minus 1 is 1, which is element of n, and done. We have shown it. Now, since S is greater or equal to 2 and S minus 1 is element of n, we know that S minus 1 is not an element of S. Why do we know this? Because if this were true, then 1 would be an element of S. Because if S minus 1 was the element of big S, then since S we know is greater or equal to 2, that would mean that 1 is element of S. But we know that 1 is not, and therefore S minus 1 cannot be the element of S. Make sense? I think it does. Okay. So now we go into the second implication for the finale, the big bang. So if we, instead of k, put S minus 1, we get that for if pk S minus 1 is a true statement, and it is, then pk, in this case ps, is a true statement. And we know that ps minus 1, in this case ps minus 1 means that S minus 1 is not in the element of S. Then we know that ps is not in the element of S. And this follows from the condition 2. So if P of S minus 1 is true statement, so this is true, then Pk plus 1 is also true. And now we know that S is not an element of big S. The little x is not element of big S, but this goes against our assumptions. Namely this part here, at least element S, our definitions. And now we have shown by contradiction that this doesn't follow. And if this doesn't follow, then mathematical induction is true. The principle of mathematical induction, the theorem of principle of mathematical induction is true. There are a gazillion uses for this. In sequences, there are like a gazillion. In combinatorics, algebra generally, like anything you can think of, it's among the most used and famous proving methodologies in mathematics. Well, now I'll be introducing you to some of the things that you might encounter when learning about mathematical induction. The first condition of mathematical induction is called the base step. It has other names, as you can see on the slide, but the most common line is a base step. The second, there are a couple of names to take note. In methodology, after you prove the base step, you go into something called the inductive hypothesis. The inductive hypothesis is a sort of direct proof, although you can show it in other techniques. But most often it's a way of direct proof in which you assume pk to be true and therefore try to prove that it necessarily follows that pk plus 1 is also true. And if you succeed in doing so, you have established or you have completed the inductive step. So showing of the inductive hypothesis is the inductive step. Taking of the inductive hypothesis is a sort of, most commonly, a direct proof, in which you are describing how the implication works, proving the truthfulness of the implication. This is pretty much all you have to know. Now we'll go over an example. We have an equality here. For every positive integer n such that this equality follows. The left side of the equality is equal to the right side of the equality, and we have to show this. The first instinct when you see these kinds of for every positive integer and equalities is to always think of mathematical induction. As the first thing you try to check is the base step. The base step is telling us that if n is equal to 1, does the equality match? Is the equality true? And if we put n equal to 1, we get 1 equals to 1 times 2 divided by 2, and this obviously follows because 1 is equal to 1. Now we have shown the base step. After you have shown the base step, you take the inductive hypothesis. The inductive hypothesis is right here. The inductive hypothesis is stating that assume that the statement, the implication, the equality in this case, is true for some k, for some number k. And after you do this, you replace every n in the equation by k. This is the inductive hypothesis. Now we get to the direct proof. And direct proof is saying that if I know that pk is true, how can I infer pk plus 1? Now you define or expand on what it means, what this statement here looks like for pk plus 1. And change k in this equation. So you change k's in this equation with k plus 1. And that results in this. So this k plus 2, this k turns into k plus 1. Following me thus far? Okay. The second thing that we do is a simple algebra. So this here, I shortened the algebra here. So if you want to see the algebra, we can do it, but I don't think that it's necessary. What we want from this equation, from this, is to get to this. So what you do is you take x times k plus 1 divided by 2 is equal to this little thing, right? To this. And then you get to what x is. And that x is precisely what is left here. And this part here, the part that we wanted, is changed by this, right? So we replace this in this equation by this. And this results in the third step. And now we just do algebra. We change sides, see what can be divided, reduced, subtracted, in hopes of finding the first statement. So if we can reduce this statement here to be equal on both sides that we have done here, this is all equal, then we have shown by a principle of mathematical induction that the whole statement is true for every possible integer n. So what we have shown is this. The first base step we shown, the second implication we have now shown. The exercise 1 is something that if someone wants to do, they can, but I will just show it. I will not be explaining it in detail. And if someone has questions about the exercise 1, they can ask me in the next presentation, the Proving Methods Part 3. It's literally the same. It's just different numbers, and it's quite it's a bit more complex because you have powers. So you have a sequence of powers, or more precisely, the summation of powers being equaling to something, some fraction. This is the solution. It's simple induction. Yeah, if anyone has any questions about it, maybe they can ask me now, but if not, I will be skipping over it. It's just a small exercise to see if you have if you truly understand what is going on. Okay, now we're going into the general form of mathematical induction. The general form of mathematical induction is trying to remove the limit of the base step, so to say. And the important part for it is precisely how we define our S, our domain of inquiry. In the first presentation of mathematical induction, our S was every positive integer. In this case, it is S such that elements of S's are integers and are greater or equal to m. In this case, the least element, so this is the crucial part, the seeking of the least element. We always have to have the least element. If we don't have the least element, we can't do mathematical induction. So if, in this case, the least element is m, because every other possible element of the set S is either greater or equal to it. The only difference from the previous presentation is that we are now starting from Pm instead of P1. And that's the whole difference. This is why it's called the general form of mathematical induction, is because it is not limited by positive integers. Every other step is the same, the names of steps is the same, methodology is generally the same. The example here is for every non-negative integer n, 2n squared is greater than n. Now we're in non-negative integers. And what did I say 0 was? 0 is a non-negative number. And since it is integer, it is also a non-negative integer. Oh, sorry. The methodology is absolutely the same. It might be a more confusing because I'm not using. It's a lot shorter here because the inequalities in this case is a bit different. We start the same. What is the least element of non-negative integers? The least element is 0. We have found the least element. Since we found the least element, we put it in the base step. Now we have done the base steps. 1 is greater than 0. Done. Base step completed. We found that base step is true. Now we are going into the base, the hypothesis, the inductive hypothesis. This is the. Where is the eraser? This is the inductive hypothesis. And since this is an inequality, inductive hypothesis must be an equality. Now we are going into the inductive step. We want to show that 2k plus 1 is greater than k plus 1. However, we can do this by the same methodology we did previously, or we can kind of shorten it. The shorter version is that we say that k is equal to 0, okay? And when k is equal to 0, this follows, right? And 2 is obviously greater than 1. This is the inequality. This is just how we got here, right? 2k plus 1 when k is 0 is 2, k plus 1 when k is 0 is 1. Now we can say that k is greater or equal to 1. And then we just put the same thing back in. 2k plus 1, 2k plus 1 is equal to 2 times 2k, which is greater than 2k. This is not obvious, by the way. This inequality is not obvious, but it follows. We can check it on Desmos and other things, but the important part is that k is greater or equal to 1, and this is true for every k such that k is greater or equal to 1 and an integer. So we don't have any funny business with minus ones and because we're non-negative integers. And this is mathematical induction proof shown. Because we have shown the step, we have shown the base step and inductive step. And tutto finito, this is done. This is the ending, because the next one is exercise 2. If someone wants to go over this exercise, we can. It's a more logic-based exercise. Well, not precisely, because it is how you prove this is by mathematical induction. But I think that your intuitions are aligning right now. Does anyone have an idea how to start this? We don't have to go over everything, like every step. Just tell me where to begin here. Does anyone have any idea where to begin with this exercise? Oh, I guess not, I suppose. Well, the first thing we have to find is that we have the least element. The least element is 2, then we're showing the base step. The base step is p of 2. The p of 2. Then if p of 2 follows, and I can tell you that it does, then we go into the induction step. We're assuming that it follows for some pk. Of course, pk must be, the k must be greater or equal to an integer, of course. An integer such that it is greater or equal to 2. And then we show by induction. We show the induction hypothesis being true. this is how it looks. And this is the end. This is today's lecture.